Okay, so we have demonstrated that if G is a cyclic group, then every subgroup H of G is cyclic. Now the contrapositive of this statement is also true. And that is the statement that if there exists a subgroup H of G that is not cyclic, then the group G is not cyclic. However, every group has at least one cyclic subgroup, even if that subgroup is the trivial subgroup. Now let G be a specific element in the group, then the cyclic subgroup generated by G is the same as the cyclic subgroup generated by the inverse of that element. And if G is a group of infinite order, then G has infinitely many cyclic subgroups. Now, from the examples that we have looked at, it would seem that every cyclic group is isomorphic either to the entire group of integers under addition or to the group of integers modulo n under addition modulo n. And this is indeed the case, and we'll prove that as a theorem. So let G be a cyclic group generated by the element A. If G has infinite order, then G is isomorphic to the integers under addition. And if G has finite order, n, then G is isomorphic to the integers modulo n under addition modulo n. So proof. We'll break the proof into two cases. So case one, suppose that for every positive integer m, a to the power of m is not the identity. Then for every distinct pair of integers h and k, positive integers h and k, where without loss of generality, we may assume that h is less than k. Since h and k are positive integers, one is less than the other. We have that a to the power of h is not equal to a to the power of k, since otherwise we have that a to the power of k times the inverse of a to the power of h, which is a to the power of negative h, which is a to the power of k minus h, is the identity where k minus h is a positive integer. And so this contradicts the condition for this case. And so for every element G in the group, G is equal to a to the power of m for a unique integer m, and hence the function phi mapping g into the integers defined by phi of a to the power of m is equal to m is a bijection. So let a to the power of m and a to the power of n be two elements in the group. Then phi of a to the power of m times a to the power of n, where we use the notation for a multiplicative group. This is the same as phi to the power of a, or rather phi of a to the power of m plus n, which is m plus n, and this is the same as phi of a to the power of m plus phi of a to the power of n, and so phi is also a homomorphism, and hence phi, which is a map from the group G into the integers, is an isomorphism, and thus G is isomorphic to the integers under addition. So case 2, suppose that a to the power of m is equal to the identity for some positive integer m. Let n be the smallest positive integer such that a to the power of n is the identity. Then, for every pair of distinct positive integers h and k, where we can assume that h is less than k, and h is of course larger than 0 since it is a positive integer, and k is less than n, we have that a to the power of h is not equal to a to the power of k, since otherwise we have that a to the power of k times a to the inverse, rather a to the negative h, which is the inverse of a to the power of h, and this is a to the power of k minus h, is the identity where k minus h is a positive integer such that k minus h is less than n, and this contradicts the fact that n is the smallest positive integer such that a to the power of n is the identity. So let s be any integer. Then, by the division algorithm, there exist integers q and r such that s is equal to n times q plus r, where r is a non-negative integer, possibly equal to 0, but strictly less than n. And so a to the power of s is equal to a to the power of n times q plus r, and this is the same as a to the power of n times q times a to the power of r, which is a to the power of n to the power of q times a to the power of r. Now a to the power of n is the identity, and so we have the identity to the power of q times a to the power of r, which is identity times a to the power of r, which is simply a to the power of r. That is, for every integer s, a to the power of s is the same as a to the power of r, where r is a non-negative integer ranging from 0 to n minus 1. And so for every element g in the group, g is equal to a to the power of r for a unique integer r in the set of integers modulo n. And hence the function phi, mapping the group G into the integers modulo n, defined by phi of a to the power of r is equal to r, is a bijection so let a to the power of r and a to the power of s be two elements in the group. Then phi of a to the power of r times a to the power of s is the same as phi of a to the power of r plus s, and this is r plus s modulo n, which is the same as phi of a to the power of r plus phi of a to the power of s modulo n. And so phi is also a homomorphism, and hence phi is an isomorphism. Phi is a map from the group into the integers modulo n, and is an isomorphism. And thus the group is isomorphic to the integers modulo n under addition modulo n. So notice that this theorem gives us a complete description of the structure of cyclic groups, in particular, if G is a cyclic group of infinite order, then this group has the same algebraic structure as the integers under addition. And if the group G is a cyclic group, of finite order, n, then the group G has the same algebraic structure as the integers modulo n under addition modulo n. So as a corollary, let G be a cyclic group of finite order n, then this positive integer n is the smallest positive integer such that a to the power of n is the identity. So proof. Suppose that G is a cyclic group of order n, then the group is isomorphic to the integers modulo n under addition modulo n. Further, the function phi, mapping G into the integers modulo n defined by phi of a to the power of r is equal to r, is an explicit isomorphism. And so phi of a to the power of s is equal to 0, that is the identity in the integers modulo n, if and only if a to the power of s is the identity in the group G, since an isomorphism maps the identity in one group onto the identity of the other. Now, since phi is a bijection, and a to the power of 0 is the identity, there does not exist a positive integer r in the complement of the singleton containing 0 in the set of integers modulo n, which is the set of positive integers from 1 to n minus 1, such that a to the power of r is equal to the identity. Now, phi of a to the power of n is phi of a to the power of 1 plus n minus 1. And so this is phi of a to the power of 1 plus phi of a to the power of n minus 1 modulo n, which is 1 plus n minus 1 modulo n, which is 0 modulo n, and hence a to the power of n is the identity. Further, n is the smallest positive integer, such that a to the power of n is the identity, since a to the power of r is not equal to the identity for r, an element in the set of positive integers from 1 to n minus 1. So, let G be a cyclic group generated by the element A. Then, the order of G is the smallest positive integer n, such that a to the power of n is the identity, and if no such positive integer n exists, then the group has infinite order, and in fact the order of the group is countably infinite, since the number of elements in the group must be the same as the number of elements in the set of integers.